Let's look at this problem. Count the number of good partitions. So this was asked in a recent weekly contest. So we are given nums array here, and in this array we are asked to create partitions such that the contiguous subarrays which are formed after partitions should not contain any element which is present in other subarray, which basically means that let's say we have created this partition. Let's use another color, and then these will be the resulting subarrays. What we are asked in this question is that if one is present here in a subarray, this one should not be present in any other subarrays. Similarly, if 5 is present here, this 5 should not be present in any of these two subarrays. So I hope the question is clear. Uh, so let's look at the approach. How can we solve this problem? So we need to create minimum possible subarray which has elements, and each element has all other instance of it in it, which basically means if one subarray contain an element, it must contain all instance of that element. So if one is given as in a subarray, one should contain all instance of one in all of the array. So for one, it's there are two instances of one in this array, and all of that is included in this subarray. Similarly, if we include 3 in this subarray, this 3 will contain this 3 also in subarray. But if we include this 3, this 5 is also in the subarray, and 5 has another instance in this whole subarray, that is here. So this should also be included in this whole subarray. So what can we first think? What is the first thought which can come to our mind? That for each element we should know the starting and the ending index at which it is present in an array. So we can calculate that first. For that we can use two maps. One will store the beginning and index, and one will store the ending index. Let that map be called MB, which is for beginning, and ME for end. And for each of the element in the subarray, we can calculate the beginning and the ending index. We will see that in a code how to do that. It's basically you will iterate through the all the subarray, and you will whenever you get the first instance of an element, you store that index in MB, and for the last wherever the last instance you get in a subarray of that element, you store that in ME. So once you get these intervals, which is starting and ending of each element, you sort this, and then you can store it in a vector, and after sorting it, you will see that our next step would be to merge it. So what we essentially mean by merging is that let's say we have 0 to as our range of first range, and 1 1 as our second range after sorting. So we see that 1 is can be merged with 0 2, and these both can become a bigger interval which contains these both. If it is possible, then we can simply merge this. Here also you will see that for 3 6, this next interval starts from 4, and 4 can be included in this interval. So we'll merge these both in one, and we will check for this now. This 5 6 can be merged in this, yes, because 5 is less than 7, so this can also be merged here. Now this 8 can 8 be merged in this? No, 8 is greater than the biggest ending here, which is 7. So it is the beginning of a new interval. So this is a new interval. And then can 9 be included in this? Yes, because the ending 10 is greater than 9. So this can be included in this interval. So basically what we have resultingly found is that there are three subarrays which can be formed using this. How we have formed these subarrays is by merging the intervals of beginning and ending index of each element. So all the overlapping intervals have been merged. Now what is our next step? Next step is to finding the number of good partitions. So once you look at this, if you have three subarrays, you will have two places for it to for you to add partition. So if you add partition here and here, there will be your answer will be this and this. Let's say you don't add this partition, your answer will be of for where you have two subarrays. Okay. So basically, what it means is if you have three contiguous subarrays, you have two places to add partition, and if you have two places to add partition, you have a choice to either add it or not add it. So basically, you have two operations for this place and two operations for this place. So resultingly, you have four numbers of partition or good partitions which you can form. So what's the formula then we get is 2 to the power n minus 1, where n is the number of subarrays which we get after merging the overlapping intervals. Another way to look at it is if you have one subarray, after that you know that there is only one good partition which is possible, that is when all the elements are included in it. Let's say you have two subarrays after merging overlapping intervals, then you have two possible choices. One is if you include 1 1 1 and 2, and other is when you include all in one. So therefore two choices. Now if you add another interval, after every interval there are two choices, either to add it in the existing one or to not add it. So that's how we get a factor of 2 everywhere. Now how to calculate this number? We can use the power. We have to create a power function which will take the base and exponent, and for that uh, it will return 2 to the power n minus 1, as we will call it. We have to create this function. We know how to solve this using exponential power method. We will look at the code how to do that, and after this we will finally get the total number of good partition for the nums. Now let's look at the code. Okay, now let's look at the code. First, let's create two unordered maps. So it's unordered map int comma int will store the nums high, and another which is the key, and value will be the index at which it is occurring. So me which mb which stands for the beginning index, and unordered map int comma int me for the ending index of that number. Now let's iterate through the nums array. And what we want to do is, if the number has not been occurred before, then we can store it as our first beginning of that number. Means we can store the index of that number as the beginning index of that number. Let's store it. as m as mb nums I is equal to I. Now, since we have stored the first index and it will iterate through all the array, and let's say if the number is 1, it will, if it finds anywhere else the number, it has to increase its index in ending map. So then we will store the ending index of, let's say, 1, and then we will store the first index of 1. Okay, now let's create a vector of pairs which will store the beginning and ending of the numbers, and then we can iterate over num and push the beginning and end in this v vector. mbx and mex. Now since we have stored these intervals with for each number, now we have to find the overlapping. So let's say the ending of uh, an interval is initialized by -1. Now let's iterate through all the v intervals in the v. So it's auto and begin and end v, and we will check if in this interval begin is greater than e, then we can safely increase our count of subarrays, and also after every interval we will check what is the ending of that interval. So if the end of this interval is greater than e, then this will become the new e for the interval. Okay, also we have to initialize count here, which will store the number of contiguous subarrays which we get after merging all the overlapping intervals. Now we can just return int power means power 2 comma count -1 modulo mod. For that we have to first initialize mod here. In question it is given, it is 10 to the power 9 plus 7. Also our normal power function won't work here because we are asked to take modulo for each we have to take modulo after each multiplication or division, like that, so that it doesn't overflow. So we have to create our own power function. We will do this by we can use a for loop and then iterate through all the powers. So let's say if the power is count -1 is 4, then we can run from 1 to 4 and multiply 2 4 times, but this will be order n solution. But we will look how to do it in log n solution, which is quite common approach. You can find it on internet. It's called exponential by squaring. So let's look how to write that. So let's return long, because the answer would be quite long here. Or int, or let's make this also long, int a, long a and long b. So if the exponent which is to the a to the power b. If b is 0, then this is the base case, we can safely return 1. Else, if the if let's say the power is even, then we can return power a into a comma b by 2. So what we are trying to do here is, if in power we are passing, we have to find 2 to the power 4. We are basically saying that this can be written as a into a, which is 2 to the power, sorry, 4, because 2 into 2 is 4, to the power b by 2. Now b is 4, so it will become 2. So this way, the recursion stack will reduce its size. We don't have to calculate for that many instances, and the depth of the tree will be then becoming log 2n. So, and also if the power is even, then we can simply do this, and if it is odd, so let's say to the power 5, then we can write this as 2 into 4, which is 2 a into a divided by v by 2, that is 2. So basically, if it is odd, we have to multiply 2 in the result. That means 2 or a in the result. So let's continue. If we have checked if the b is even, then we have to do this in this way, and else if it is odd, we can return a as seen above into power a into a comma b minus 1 by 2. Okay, now so let's take mod everywhere so that it doesn't overflow. And here also we have multiplying, so here also not. Okay, let's try and run it. Okay, it got accepted on the test cases. Let's check for all cases. It got accepted. Thanks for watching.